This is Dr. Hanaa Assil, and this is IGCSE Chemistry, Cambridge. This is the first lesson, and the first lesson is about states of matter, solid, liquid, and gas. We know that matter is made up of very small particles that are in constant motion. This is what we call a kinetic particle theory. We say that the particles are constantly bumping into each other and moving around from one place to another randomly in the container. This is called Brownian motion. So we say the Brownian motion is the random motion of particles resulting from their collision with atoms or molecules when suspended in a gas or a liquid. Looking at the different states of matter, we're supposed to know the arrangement of particles and the movement of particles. When we talk about arrangement, we need to state whether the particles are near, far, close to each other, touching each other, and whether there is a certain regular arrangement or not. For example, what's the arrangement of particles in a solid? In a solid, particles are arranged in regular rows, close packed. If we're talking about a liquid, we say that particles are near to each other in clusters, and clusters means in groups, not in any particular order. For gases, the arrangement is particles are very far apart, random arrangement. If we're talking about movement of particles, the solids, particles vibrate in fixed position. Remember that we cannot say that particles do not move. All particles are in constant motion. So in a solid, they vibrate in their fixed position. For liquids, the particles move around each other in a fixed volume. For a gas, particles move in fast, free, random motion. If we're talking about which one is compressible, which one has fixed volume, which one has fixed shape. So, compressible means will the particles be able to come nearer to each other. So in order to be compressible, the particles have to be originally far apart from each other. For a solid, the particles are not compressible because they're already touching each other. For a liquid, the particles also are not compressible because they're very near to each other. The particles of a gas are compressible because they're originally very far apart, so you can press them nearer to each other. Which one has a fixed volume? The solid has a fixed volume, a certain amount that does not change. A liquid also has a fixed volume because the amount of liquid, whether you put it in a beaker or in a flask or in a bottle, whatever container, it is still the same volume of liquid. But a gas spreads through the container, so it takes the volume of the container, so it doesn't have a fixed volume. Now, which one has a fixed shape? For solids have a fixed shape. The liquids have a fixed shape. They usually take the shape of the container, so they do not have a fixed shape. Gases also take the shape of the container, so they do not have a fixed shape. So a question could say much more oxygen can be stored in the tank when oxygen is a liquid rather than a gas. Give a reason for this in terms of arrangement of the particles. So he's saying if I were to put oxygen into a tank, I will have more of it if it's a liquid rather than a gas. Of course, this is because as a liquid, particles are more closely packed, so more particles can be placed in a certain volume. We can change from one state to another. So if we have a solid, we can heat it, it changes into a liquid. When a solid changes into a liquid, that is called melting. So if we were to say what is meant by melting, melting is the change of state from solid to liquid. This happens at a specific temperature, which is called the melting point. So the melting point is the temperature at which a solid changes to a liquid. So once we have heated the solid and it becomes a liquid, we can continue heating it until it becomes a gas. When we heat a liquid and it changes into a gas, that is called boiling. Boiling is the change of state from liquid to gas, and this happens at a fixed temperature. We can also say that it is evaporation, but evaporation is the change from liquid to gas also, but at any temperature. Boiling would happen at a fixed temperature. Evaporation happens at any temperature, and it occurs only on the surface of the liquid. So for example, if I'm heating a beaker of water, 20 degrees, 30 degrees, 40, 50, 60, it's not boiling yet, but you can see water vapor. So this is because the water is evaporating at all of these temperatures. If we were to go the other way around, we cool the gas down, it will become a liquid. When a gas becomes a liquid, this is called condensation. So condensation is the change of state from gas to liquid. If I continue cooling the liquid, then it becomes a solid, and that is called freezing. Now, some solids, when we heat it, it does not change into liquid. It changes into a gas directly. So this is called sublimation, when the change of solid changes directly to a gas, or a gas changes to solid without passing through the liquid state. This is called sublimation. This happens in some cases, for example, in cases of iodine or carbon dioxide. When we heat iodine, solid becomes a vapor directly, cooled, it turns back to solid. Carbon dioxide gas, also when it is cooled, it becomes a solid directly without passing through the liquid state. So this question says 3 states of matter are solid, liquid, and gas, and we have diagrams of the beakers containing solid and liquid and gas, and he's asking what is arrow X, Y, and Z. Remember, look at the direction of the arrow. So X is going from liquid to gas. Going from liquid to gas is boiling. It can also be evaporation. If you say it's evaporation, that's fine also, but usually we say it is boiling. Going from gas to liquid, that is cooling the gas to become a liquid, that is called condensing. Going in the arrow Z from liquid to solid, going from liquid to solid is freezing. This is another question in which he has diagrams of the particles in the 3 states of matter, and he's saying use letters X, Y, and Z to give the starting and finishing states of matter for each of these changes. Now, if I'm talking about ice changing to water, ice is the solid form, water is the liquid form, so we're changing from solid to liquid, that is from Z to Y. If we're saying I want to change from solid iodine to iodine gas, solid, that means it is Z, and it's changing into gas, that is X. Molten iron to solid iron, remember that molten means the liquid form, so that means that the iron has been heated until it has become liquid, that is molten iron. So changing from molten iron to solid iron, that means I'm changing from liquid to solid, so that is from Y to Z. Ethene to polyethene. Now, if we haven't done organic chemistry yet, ethene is a gas. It changes to polyethene. Polyethene is basically what we call plastic, so that's a solid. So changing from ethene, that's a gas, to polyethene, that's a solid, that is from X to Z. Okay, what happens during melting, or what happens during boiling? So when something is melting or boiling, you're heating it. When a substance is heated, particles gain kinetic energy, move faster, overcome the attraction forces between them, and move further apart. So this is what happens when you're melting or boiling something. What happens the other way around when we're condensing or freezing? For a gas to condense or for a liquid to freeze, you need to cool it. So when a substance is cooled, particles lose kinetic energy, move slower, come nearer to each other. This is another question. He says heating a liquid causes it to become a vapor. What happens to the molecules of the liquid during this process? Remember that in IGCSE Cambridge you have 3 papers. The first paper is the multiple choice, which is paper 2, if you're in IGCSE grade 10. So the multiple choice here, you're supposed to choose A, B, C, or D. What happens to the molecules of the liquid during this process? Do the molecules become bigger? Remember that when we were changing from solid to liquid to gas or the other way around, we did not mention anything about sizes of molecules because the sizes of the molecules do not change. They do not become bigger or become smaller. So saying that molecules become bigger, no. So my answer is either C or D. Now, do the molecules move further apart? What are we changing? We're changing from liquid to vapor. Yes, the molecules are moving further apart when they change to vapor. So my answer is C. Another question could say, describe the changes in arrangement, movement, and energy of the particles when the liquid wax cools to become a solid. So here we're talking about a liquid cooling, becoming a solid. What happens to it with respect to arrangement, movement, and energy? We should know that if we're cooling the liquid, particles lose kinetic energy, move slower, come closer to each other, and become a regular arrangement in rows. If we have a solid or a liquid or a gas at room temperature, what does that tell you about its melting point or its boiling point? Or if you're given the melting point and boiling point of a substance, you can determine whether at room temperature or at a specific temperature, whether this substance is a solid or a liquid or a gas. So let's say a substance is a solid at room temperature. So for example, a piece of iron is a solid at room temperature. What does that tell you about its melting point and its boiling point? It's a solid at room temperature. That means that at room temperature it has not melted, it has not boiled, and that means that its melting point and its boiling point are higher than room temperature. So if a substance has a melting point and boiling point higher than room temperature, that means that at room temperature it was a solid. If I have a substance that's a liquid at room temperature, now a liquid means it has already melted, but it hasn't boiled yet. So that means that its melting point is lower than the room temperature, but its boiling point is higher than the room temperature. If a substance is a gas at room temperature, that means that at room temperature it has already melted, it has already boiled. So its melting point and its boiling point are below room temperature. So here, this is a question that gives you the melting point of 3 substances. He's saying that the boiling point of all these substances is above 100. So give the physical state of each acid at room temperature. When he's talking about capric acid, he says that the melting point of capric acid is 32 degrees centigrade and its boiling point is 100. Now, if its melting point is 32, that means at room temperature, which is 20, or sometimes room temperature is regarded as 25. But at room temperature, it hasn't melted yet, so capric acid must be solid. Now, formic acid has a melting point of 8 degrees centigrade. That means that at room temperature, at 20 degrees centigrade, it has already melted. Its boiling point is above 100, so it hasn't boiled yet. So that means that formic acid must be a liquid. Palmitic acid has a melting point of 63 degrees centigrade. That means at room temperature, it hasn't melted yet, so it must be a solid. Another question says, melting points and boiling points of 4 substances are shown. Which substance is liquid at 100 degrees centigrade? Remember that he's saying at 100 degrees centigrade. Now, for a substance to be a liquid at 100 degrees centigrade, that means it has already melted, so its melting point must be below 100, but its boiling point should be higher than 100. So the one that has a melting point below 100 and boiling point above 100 is substance C. We have to understand heating curves and cooling curves. A heating curve means I'm starting at the bottom of the curve. My substance is a solid. I'm heating it. As I heat it, the temperature increases. As the temperature increases, it is still a solid because it hasn't reached its melting point yet. But once it reaches its melting point, then it starts to melt. It starts to change into a liquid. Now, while it is melting, the temperature is not increasing because any heat that is being provided is being used to change the substance from solid to liquid. So the flat area in the heating curve indicates the change of state. So that first flat area at the bottom indicates melting. Now, as we go up, all the solid has changed into a liquid. So now the temperature starts to rise. As it rises, it is still a liquid, but it hasn't reached its boiling point yet, so it hasn't boiled. Once it reaches its boiling point, the temperature becomes constant, and you have another flat area for boiling, and that means that during that time, any heat that is being provided is used to change the liquid into gas. Once all the liquid has changed into gas, then the temperature of the gas starts to rise. Going the other way around, if I start with a gas at the top and I cool it, then as we cool it, the temperature decreases until it reaches a temperature when it starts to change to liquid. So that's condensation. Now, while it is performing condensation, changing into a liquid, the temperature remains the same, which we call the condensation point. Remember that the condensation point of a substance is the same as the boiling point. Now, once the liquid is cooled further, the temperature decreases until we reach a freezing point, and at the freezing point, the temperature remains constant until all the liquid has changed into a solid, and then the temperature of the solid begins to decrease. Diffusion. What is meant by diffusion? Diffusion is the movement of particles from an area of high concentration to an area of low concentration down the concentration gradient. That means if I have a crystal of potassium permanganate, which is purple in color, and I put it at the bottom of a beaker of water, then the bottom of the beaker has a lot of potassium permanganate particles, so that is my area of high concentration. The top of the water has very little potassium permanganate particles, so that is area of low concentration, and the gradual change in concentration from high to low is called the concentration gradient. Now, the particles will start to move from the area of high concentration at the bottom of the beaker towards the area of low concentration at the top of the water. It continues to do that until the particles are equally distributed throughout the water, and we have an equal distribution of the purple curve. Another case is where we have bromine. Bromine is a liquid, and we put it in the jar at the bottom, and we remove that cover between the two jars, so we allow the particles to move freely. Now, what is happening? The particles of liquid bromine gain kinetic energy, and this is from the atmosphere. They move faster, overcome the attraction forces between them, so basically the liquid changes into gas. Then the particles move from area of high concentration to area of low concentration by diffusion, and eventually both jars are filled with the brown color. We also have diffusion of liquid in liquid, so if I put a drop of ink, it will move throughout the water until there is an equal distribution of the color of ink all through the bowl of water. An application of that is when we have a cotton wool soaked in ammonia on one end of a open-ended tube, and on the other end we have a cotton wool soaked in hydrochloric acid, HCl. We close the ends of the tube. We allow the particles to diffuse freely. So the particles of ammonia and H3 will diffuse away from the cotton wool with high concentration of ammonia, so it diffuses to the other side. The HCl particles will diffuse from the cotton wool that has hydrochloric acid towards the other side. Now, if they are diffusing at the same rate, they should meet at the middle of the tube. But actually we find that when they meet and form a white cloud of ammonium chloride, this happens nearer to the HCl particles. And that is because the HCl particles are moving slower. Now, what determines the rate of diffusion of the particles? The main factor is the mass of the particles. If we look at the different particles of ammonia and HCl, the one that has lighter particles, lower molecular mass, will diffuse faster. If you don't remember what's molecular mass is the addition of the masses from the periodic table. So NH3, nitrogen is 14 plus 3 for hydrogen, so the molecular mass of ammonia is 17. While HCl, the hydrogen has a mass of 1, the chlorine has 35.5, so the molecular mass of HCl is 36.5. So the HCl particles are higher molecular mass, they move slower, while the ammonia particles are lighter, lower molecular mass, so they diffuse faster. Another factor that will affect the rate of diffusion is the temperature at which this is happening. So if the particles have more energy at higher temperature, then the particles will move faster. So if I were to hold this tube with my hand, so that provides more heat from the body, this would cause the particles of both NH3 and HCl to move faster, and the appearance of the cloud of ammonium chloride would happen faster. So energy at higher temperature, particles gain more kinetic energy, move faster, diffuse faster. Another factor that affects the rate of diffusion is the nature of the medium. So particles that are diffusing in gases would diffuse faster than if they were diffusing in liquids. Remember that diffusion does not happen in solids. You cannot have something diffusing through solids. A question from the multiple choice would say some sugar is dissolved in water, which diagram shows how the particles are arranged in the solution. Remember that once we have diffusion, the particles are randomly distributed through the liquid. So they're not just on the sides like A, they're not only at the bottom like C, they're not only at the top like D, they are randomly distributed through these, so my answer is B. Another question says a gas jar of bromine vapor and a gas jar of air are set up as shown. The glass slide is removed. Diagram 2 shows the appearance of the gas jars after 1 hour. Which statement explains why the bromine and air mix together? Now we said if I remove the glass slide, then the bromine will diffuse through the jars and become equally distributed. This is because what? Bromine is denser than air, or bromine is lighter than air, or bromine molecules move upwards and molecules in air move downwards, or is it because molecules in bromine and air are moving randomly? Remember that this is because molecules in bromine and air are moving randomly, so your answer is D. An application of that is in separation of gases. So when we have a mixture of gases, for example oxygen and chlorine, the one that is lighter, lower molecular mass will diffuse faster. So we have two tubes in this case. We have an inner tube and an outer tube. The outer tube contains a mixture of oxygen and chlorine, and the inner tube is what we call a porous tube. A porous tube means it has tiny little holes that allow gases to diffuse through. So, which gas will diffuse into that porous tube faster? The one with lower molecular mass. Now, if we calculate the molecular mass, we find that oxygen has lower molecular mass. So more oxygen diffuses into that middle tube through the porous tube, and that tube will now have mostly oxygen, while the outer tube now has mostly chlorine. And that is the end of the first lesson. Thank you for listening.